Welcome back to the Pythagorean Theorem Part 2, the revenge of triangles. In this video, we're going to be taking a look at two more examples of the Pythagorean Theorem. They're a little bit weirder, so I wanted to make sure I had enough time to be able to talk about them. In addition to that, this is the video I promised we'd get into things like number theory. So we are going to be looking at something called irrational and rational numbers and how to estimate a really tough square root. And we're going to be taking a look at how to do that on like a number line, okay? So here we go. Pythagorean Theorem Part 2.
Here is a grid. On the grid there are points A and B, and we are tasked with finding the distance between the two of them. This seems rather tricky because we don't have a lot of information here. Or do we? I mean, if the points were on the same line, like C and D, we could just count the segments between them to find the distance, which is 2. Same with C and E. I can count the distance between them, which is 3. But if we wanted to find the distance between E and D, we're stuck, because the 2 points are not on the same line, causing the distance between them to be diagonal and difficult to measure. Like if you're us, tracing these distances has formed a triangle, a right triangle, with a missing hypotenuse. So, returning to the original problem, start by tracing the distance between A and B. This is your hypotenuse. To make the legs, we trace along the given grid lines to make the right triangle. This problem is kind of cool because we have to use the grid to find the length of the two legs, because it's not being given to us. Once we have these values, it turns into a regular missing hypotenuse problem. The missing hypotenuse turns out to be the square root of 20. For this example, I'm going to be giving a decimal answer. I'm going to plug the square root of 20 into a calculator and round off to the nearest tenth. This should be 4.5, and that's my bad. This gives me my final answer. The distance between points A and B is 4.5 units, not 4.4. There are also problems where our well-behaved right triangle somehow ends up in the third dimension. In this example, the right triangle is stretched between opposite corners of a box. Usually when solving the Pythagorean Theorem problems, we only have 2 dimensions to work with, so our equation only has 2 legs. However, with the triangle stretched over 3 dimensions, we have 1 additional leg to consider, which means our equation has 1 additional leg to consider. Aside from this, the problem is then solved the same way. For this example, let's say the leg lengths are 2, 3, and 4. I plug in the values I know and solve for the unknown. The missing hypotenuse is revealed to have a length of the square root of 29. In previous problems, when I get an answer like the square root of 13, I've left the answer either as a square root or I've used a calculator to find the exact answer. But there is also a way that you can use your gigantic brain to estimate the square root of 13 if your calculator is not working or the calculator is forbidden. To start, make a number line between 1 and 10. These numbers are going to be our roots. Above the number line, we are going to write in all of our squares, or in other words, we're going to square each of our roots. Now that we have our squares and our roots, we can find where the square root of 13 belongs. The square of 13 lands between the square of 9 and the square of 16. That means the square root of 13 will fall between the roots of 3 and 4, which means that the square root of 13 is roughly a number between 3 and 4, which is roughly 3.5. Let's use a calculator to check our estimate. Calculator says the correct answer is 3.6, so our estimate was very close. Another example. Let's estimate the square root of 60. Pause the video to see if you can guess it. Once again, we find where the square root of 60 would fall, between the numbers 49 and 64. Which means the square root of 60 lies between 7 and 8. However, this time, because the number 60 is a lot closer to 64 than it is to 49, we're going to move the decimal a little bit closer towards the number 8. We estimate the square root of 60 is roughly 7.7. Checking on the calculator, and bam! 7.7 is a great estimate. These tricky square root values is an example of something called an irrational number. We're now going to define what makes a number rational or irrational. Rational numbers are numbers that can be expressed as a fraction. So right off the bat, any fraction is going to be a rational number. The next type of rational number is something that is predictable, such as a repeating decimal. A decimal that has a repeating pattern is easy to predict and so is rational. Another rational number is the square root of perfect squares. Or in other words, if the square root of the number is an integer, then it is a rational number. Now let's take a look at some irrational numbers. The number pi is irrational because it continues in a seemingly random way forever. This makes it impossible to turn into a fraction, and so it is irrational. The second type of non-repeating decimal, similar to pi, a decimal that is infinite and does not repeat cannot be turned into a fraction, so it is irrational. The last type we'll look at here is the square root of imperfect squares. These are the tricky square roots, like the square root of 13 or 60 that we estimated previously. These numbers continue infinitely and cannot be turned into a fraction. Most of the time, when you are asked a question about rational and irrational numbers, it simply wants you to classify what that number is. The first number is a decimal that ends and doesn't repeat. That is a dead giveaway that it can be a fraction, which makes it rational. The square root of 100 is a nice clean 10, so it is a square root of a perfect square, and a rational number. A repeating number is predictable, or I know what's going to come next, so it can be turned into a fraction. Another rational number. A non-repeating decimal cannot be predicted, and so cannot be rational. 7/2 is simply a fraction, which automatically makes it rational. And finally, the number 12 is not a perfect square, so the square root will not be predictable, making it irrational. Now, I mentioned before that a repeating decimal can be converted to a fraction. However, this is tricky because the number repeats infinitely. To solve this problem, we are going to use the magical denominator of 9. Starting off, 1/9 creates a decimal where the number 1 repeats. 2/9 creates a decimal where the number 2 repeats. So for example, if I wanted to create a decimal where the number 3 repeats, what do you think my fraction is going to look like? Following the pattern from before, we would use 3/9. What if I wanted to have the number 10 repeat? I would just put 10/9. But when I put this into the calculator, it's not the number 10 that repeats, it's back to repeating the number 1. How do we get the number 10 to repeat? The answer is that we change the denominator from 9 to 99. The number of 9s in the denominator tells you how many digits will repeat. Because the number of 10 has 2 digits, I need 2 9s in the denominator to cause the number 10 to repeat. This means if I want a 3-digit number to repeat, like 567, then I will need 3 9s in the denominator. This pattern will work with any amount of repeating numbers. One last thing. Remember that if you don't want a number to repeat, it is placed over the proper tens value. Like if I don't want the number 56 to repeat, I put it over 100 instead of putting it over 99.
And that's it. That's all the Pythagorean Theorem stuff, at least for 8th grade. For now, you should be at least set for a little while, until next year. And then you'll have some more stuff to learn about the Pythagorean Theorem, because like triangles have an entire study based off of them. It's crazy. There's like 3 sides to them, and there's endless proofs about them. Yeah, I'm gonna go make microwave taquitos.